It's very nice. I like it.
Oh,
Something
good.
stuff. It just knocks me out.
We could, well, there could be a few of those, you know.
They were good, weren't they?
That was very good at lunch.
They were only 3.5% this one, which was a much better idea.
Okay. We're ready for our next talk, which is Nick Rossiter, who works with Mike Heather, as we know. The universities in Chetler, I used to think they were the same person.
We never appeared together.
Even at the same conference, they weren't there at the same time. But I did manage to snap them outside of the Travelodge together on one occasion.
There was Michael wearing his underpants outside his trousers.
I was being the chairman.
So the universe's intention, an expressive dynamic information and communication system as extension. Okay.
Right, thanks very much. Right, so this, we did give a talk on music at the last ANPA, and so this is a continuation of that. I've got a slide which shows we've been fairly busy on the topic. The expressive dynamic information and communication system is, we have the example of music, and so I'll get on to what I'm doing. Yeah, so further work since last August. Well, we got the paper using category theory to represent information systems, more like database systems, that's been published in the current ANPA. And so that was quite an improvement because we actually developed the details of the data structures. Done a literature review. I feel having told students for years they should do literature reviews. I've finally done one on this just this weekend. I've done some field work. That's been the most interesting bit, actually studying the orchestra, how they work, and also had some advice from one member of the orchestra in particular. Been to a couple of other conferences, Unilog 2018 in Vichy, where I presented a paper on the workshop Logic and Music, so that was good to meet people working in the field. And then I went to Daniel Dubois' Anticipator Systems in Baden-Baden 2 weeks ago, so presented some things there. And obviously this has resulted in quite a lot of technical issues being raised. So the data structures section has been revised, particularly with intention extension, and the process section is revised, hopefully making it more orderly, bringing a bit of brain activity as well, which is a bit speculative, but Walter Schempp, who was at the Baden-Baden conference, was moderately appreciative. He actually, that was good. And he also introduced anticipation, and of course you'll know that comes from the Baden-Baden conference, because that's the purpose of the Baden-Baden conference. Yes, so I'll have to acknowledge members of the Royal Northern Symphonia. That's our local symphony orchestra in the northeast of England, Gateshead, and in particular Alexandra Rekalina, who's a sub-principal first violin, so I've had some input from members of the orchestra. But she's a violinist, and I have to make a qualification there that some of the work I have is actually rather specific to the violin. And when I look at other instruments, they are well, violin's formidable enough, but they have different characteristics, so I think that's a qualification. So we take on the challenge of a testing application. Databases is basically does have a very simple principle, but it's not expressive. So if you had an expressive bank statement with amounts altered a bit and things like that, some wayward approach, you wouldn't be happy with it. And so database systems are not expressive. The idea was to try and develop the ideas on databases into a more expressive information communication system. And the two concepts that come out in category theory are the monad, which represents process operating in a topos, within a topos, and the topos, which is the structure. So the monad is akin to a program, something like topos is a data structure. Based on you can do that. Good. And we're going to look at previous work using category theory of music. Right, natural's a word that's used everywhere now, and of course our title is Alternative Natural Philosophy. And one thing that was very interesting at Universal Logic was that they don't use the term adjoint so much now, they use the term natural relationship. And that's creeping in as a less formidable way of representing things. So natural is, and of course the great thing about music is a composition of notes. You call it, and you write a composition, you compose. And so this is, and you've got rules as to how you compose the notes. And category theory is a composition of arrows with rules. So there should be some natural match there. And so we're going to use the top levels of category theory, closure over 3 levels. You don't need any more. We want to have expressiveness of the data structuring, particularly with things like intention, extension. But above all, this characterises the work to some extent. We want to capture the process of performing music. So we're not writing music here. We are really looking at performing music and capturing the structure of music and its performances at this stage. It could be used, I think, as a composition tool, but that's not been our main aim. Be more interested in performance. And that's with the monad operating within the topos. Right, so let's have a look at some of the earlier work. Henry Klumpenauer, American, I think. He was a student, PhD student of David Lewin, and they didn't actually use category theory, they used nets, and they're called K-nets and L-nets after their surnames. And these are really a bit brute force to music. They're transformations from one pitch class to another. So that's basic. And you have a graphical technique, and they have isographs to represent where things are apparently equal or similar. So, and they're based on the classical harmony, based on Z12. That was another interesting thing from the Vichy conference. The music people there said, you're very brave using the violin at all, because you get into real numbers there. We always prefer the piano, because you're restricted to the notes you can actually play, and it's actually easier to do the theory for something like that, if it's keeping more or less to an integer format. So this was the idea, this was really network, not category theory. And then we had some further work. I don't know if you've ever looked at this book, The Topos of Music by Matt Solar. It's 1,338 pages, so I haven't brought it with me. And it's an amazing book. It does develop functorial denotators based on K-nets, and it develops this idea of digraphs, which are these graphical structures. And it does a tremendous amount on theory of music. But the title is misleading because there's not a lot on the topos and music. So it tends to be a rather disjoint treatment. Deals with the topos a lot and deals with music a lot, but doesn't actually bring the two together, which I think was a bit unfortunate. So it's a rather difficult publication to read, but it's got a splendid index. The index must have been done by the author, and so you can actually find things in it very well. So I wouldn't discourage people from buying it. And Matt Solar and Andrietta, 2006, went on to develop the denotators idea, and this really was the state of the art at the time. So you have pitch classes based on Z12, that's the 12-note scale. The vertices are pitch classes and the edges are transpositions, and you construct a digraph. And they did some extensions to the earlier work. They had a 4-tuple for articulation, onset, pitch, loudness and duration. So they started bringing in articulation and how, of course, one performance is not the same as another. They used power objects to represent chords. So a chord is a subset of is a power object in the set of pitches. And they made paths through the music as well, so you can see where you're going. And if I say the bit at the bottom is what they appear to base their work on the Island Moor category, but they haven't actually stated that. So they've done a homemade version of the Island Moor theory, which is very commendable. I don't think there's any dishonesty here or anything like that. And pullback of the category of pre-sheaves on the Clydesdale category are on the Oneida embedding, and that is not too dissimilar from the approach we use. So it's actually, it's a lower level description of what we've done. So I thought that was really the quite a good advance, and Matzo was involved in that. Why he didn't include this in his book, I don't know. And then we come to some familiar category theory names. Andre Erisman, of course, as the wife of the late Charles Erisman. And so Alexandra Popov, Charlotte Kolosegon, Marina Andrietta, they've carried on doing their music development. Andrietta is very keen on jazz and popular music, so there hasn't been an effort to actually stifle, just to make it pure classical. And I think that applies to other advances. And they developed the PK nets, which gives more flexibility in the structure of notes. There were some problems with cardinalities in the earlier version, they've been removed. And the labelling is flexible for different genre jazz, etc., things like that. So they're now actually formalising it in category theory, and they do the right thing in having a natural transformation, which takes it up to 3 levels. In category theory, you have 3 levels. You have the category containing the arrows, you have a functor mapping the arrows in one category to the arrows in another category. And then you have the natural transformation, which maps a functor to another functor. And when you do that mapping with the natural transformation, you achieve closure. You have defined something as unique up to natural isomorphism. And then the word natural comes in again. So that's in fact the underpinning of a lot of category theory, to define things as natural, meaning they're unique, defined uniquely. Shortly after, they had an afterthought on this, and they replaced the set with the rel category for relationships, but we use pullbacks for relationships. So I don't think that the rel is really very much like a database relation.
Is that the rel A set? Is that the
REL?
The
It is a. I don't know if it's in there.
rel A? No.
No, I don't think the claim uses it very much.
Okay.
No, but it is there. So feelings on earlier work. Well, there's obviously sound advance in basic musical structures. Some of the work we would describe as categorification. In other words, it's not looking at what category theory can do for you from scratch. It's taking existing set theoretic methods and converting them on a one-to-one basis to category theory, which works to some sense, but maybe you're not taking the best advantage of category theory. So we think there may be more natural methods for composition, data structure with topos, and the process or communication for which we use the monad. And as I said earlier, that on denotators in 2006 comes closest to us. And in fact, the Clydesdale thing you will see at the end of this talk, the Clydesdale lift. But it's a good get out, this, in some respects, because we haven't done much work on the basic structure of a score, and the PK nets or denotators could be used as our bottom level, our lower level. So there's nothing wrong with what they've done there, and we could use those as some other representation. So that's the literature review. Now if I were a supervisor, I would look up the title of the student's paper or thesis in the literature and then say, look, is this not relevant? I'm going to have another go.
When I read mark student dissertations, on the review, I look at the referencing to say that no.
Yes. Yeah, of course you can cite stuff which is just a bit banal. Yeah. Right, so the aim is a topos. A lot of the category theory terminology comes from the classics. So, of course, topos was from Aristotle. used as a term for a placeholder. If you think of it as a topic, it's not a bad idea. It's really where you have your data structure on a particular area. And at Vichy, they were talking very much, you construct your topos world, and then you live within the world, and the process is within the world. And so it is really constructing your own world. It's a basic idea. And then, of course, Cartesian, well, that comes from Descartes, and that's another. Cartesian, I'll explain that now. Obviously, you want relationships between things, and relationships are expressed in this form. Locally Cartesian closed category means it's a pullback, but it has some added properties and facilities. So this Cartesian closed category, you have relationships within the product, you have pullbacks and limits. Pullbacks and limits are used interchangeably by a lot of people, but in fact, and I have done that in this talk for the first time, I've actually separated out the limit from the actual product, the pullback.
You want to explain what the pullback is?
Yes, I've got the pullback in, but I put the limit in as well, because the limit is actually the fundamental property of it, because that has the universal arrow onto the product. The product. I'll show you the diagram soon. What I mean. So, but I'm afraid I probably will still drift a bit when I'm speaking between pullback and limit and push out and co-limits. But so you have connectivity, exponentials. You can't have stray objects lying around in a category. Everything's got to be connected.
When you say exponential, do you mean exponential function?
Exponential is where, yes, it's a currying thing where you, like 2 to the x means all the arrows from x to 2.
Okay.
So you have these exponentials in the category.
It's e to the x. Is that what I mean?
No, well, x is perhaps a bad example. You could say a to the power of b would be all the arrows from b to a. So you do that for all the arrows, all the arrows in the category. Internal logic of a Cartesian closed category is a lambda calculus, which is widely used. The identity comes from the limit, so we have identity. We also have interchangeability of levels, so if I put a node in, it could be an object or it could be a category object, meaning that that object is another category with structure of its own. And we have this word hyperdoctrine, which comes from Lorvier, which gives you your standard quantifiers, like the existential quantifier and the universal quantifier. So this gives you your logic across the diagram, and of course that's very important for doing manipulation. And the other thing about an LCCC is that you can decompose a node into other categories below, and those other categories have to also be locally Cartesian closed categories. So it gives a uniform approach to structuring data, which is relevant for applications such as this.
So I take this to classical logic and objects. The hyperdoctrines are a set of things that are like axioms.
Yes.
And the categories are like objects, but they might be complexified objects.
Yes.
So are the relationships then, are they also a kind of axiom? Or
Well, the relationships across the structure.
Right, so
They go from the product to the code to the plus end. Go from the times end to the plus end.
So they're like a differential in some sense, or a transformation in some sense.
They're not a transformation. They're more an existence.
Existence. Okay.
Giving your existence. The main one of these arrows across is delta, which maps from the, say you're relating A and B, which maps from A and B separately into the product A times B. Yeah, so that's the diagonal, and then you have two opposite ones. Yeah.
Right.
Yes, so if you want to get a topos, that's a bit more sophisticated. You can think of topos broadly as a category with set-like properties. So it's very nice for people to think that way. So if we had a definition of relationships within a co-product, you need a co-product end to be specified as well. The plus end has to be closed as well as the times end. In a pullback, the times end is closed. If you want to have it into a topos, you have to actually close the plus end as well. The language then becomes the internal intuitionistic logic, which is sometimes known as heighting. And you can have a query facility, the sub-object classifier, for searching the topos. And you can also have a reflective sub-topos viewpoint, which is a view. You can't really take a subset of a topos, because that violates the universe principles. You can identify a subset of your topos, but you cannot isolate it.
So you can't have a topos, nested topos.
Lesser top.
You can't have a nesting of top I.
I think you could. Yes, I think you could take your subtopos and give it a name. It's a view. And then you could define it. Yeah, I think as long as you keep them as views, they are all right.
Right, so you don't mix definitions within the subgroup, so
No.
there's no interrelationship between them. So there's a natural boundary.
Yes.
Okay.
Yeah.
When you say isolate, what do you mean by isolate? Is that a transformation?
Isolate. I mean, it's like in a relational database. If you select the data and then you put it into another file, that would be isolating it.
Oh.
Put it into another table or something. You're actually pulling it out of the structure. So we get a topos, Aristotle. That's the basic idea. So topos for music. Music is viewed as a communication of some manuscript by communicators. Topos is relatively static, but nothing is obviously static in this musical world. You've got an orchestra, that's going to vary, and as we shall see, the manuscripts vary and things like that. So it's actually very fluid, all of it, but it's the performance that potentially varies in the short term more than anything else. So the monad is dealing with the process, the topos with the relatively static stuff. And if we deal with a manuscript, that comprises scores, other intentions of composers and writers, and that includes the musical notation or more spontaneous formats. It doesn't have to be slavishly in the way it's normally laid out. And the communicators, of course, are the performers and other aspects of the performance. So it includes an orchestra, group, recording company, something like that.
And audience.
Yeah, I should have. I love that. Audience is very important. They do get a feel from the audience as to whether. Yes, that is very true. Yeah.
People I know who in audience.
They're no audience. They probably wouldn't play as well.
Pissing off a cliff.
Yeah, I'd agree with that. So come on to intention extension, which again comes from Aristotle. He was a very wise person, Aristotle, when it comes to data structuring. And, well, most important feature in music, I don't think a musician would agree with that, arguably the most important feature in music from a data person's point of view. Terms come from philosophy, they're used in philosophy. In mathematics, computing science, the intention is the type, that's the general, and the extension is the specific, the collection of instances that satisfy the type. There's some semantic dimension to it, though, when you use this intention extension. It's not the same as data structuring a hierarchy of types. Otherwise, you could end up with a ridiculous long list, long hierarchy. So, but this, I think, should be done first to try and get a view of the semantics of what you're doing, while you're doing it. So, this is important. So, the universe contains everything. And the universe of discourse is that section of the universe of interest to our application. So we're not isolating any part of the universe here, we're identifying that part of the universe that is relevant for our work. So the intention is the universe, and the extension is the world of music, universe of discourse. So that will contain all the things in the universe that we think have some relevance to music. I'm not saying this is closed. As we've already seen, the audience has had to include the forward.
We're not here.
So I think that it's really quite open in many respects. I think it's worth looking at a score. A lot of people think classical music, a score is very fixed item, and people have been playing it the same way since 1750, say, or something like that. But that's far from the case. A musical manuscript has both intentional properties as a type for how the work is to be performed, so it is like a type there according to the composer. But we get a lot of complications which I would class as extensional properties of the manuscript. We've got instances of the manuscript of various forms, various dates. The publications can vary. They can be composer initiated. A composer can decide he doesn't like this bit, he's going to replace it by something else. Quite often you get developments after the composer's death when people say, oh, I don't think he really meant that. And Herbert von Karajan of the Berlin Philharmonic was notorious for saying things that, oh, I think the composer must have been on an off day. I've replaced this section with that. But if you go to a rehearsal, you also see that the conductor, well, like von Karajan, has very definite views as to how it should be played. And the members of the orchestra, they dutifully scribble on their scores as the rehearsal goes on, when the emphasis is different perhaps, or something like that. And for the performance, no two performances are ever the same, so you're always going to have some flexibility there. So a musical manuscript is extensional to the universe of discourse and music, one of the objects in the universe, but intentional to the manuscript's variants and performances, defining the underlying object. So you can get very elaborate intention-extension hierarchies. Category theory suggests 4 levels are adequate, 3 levels of mapping. 3 levels of mapping is always what category theory suggests is sufficient. But if you construct more, it doesn't matter. But it doesn't actually give you any more ability in the maths. They are superfluous. Right, so let's have a look at a pullback now. So relationships in category theory, they can be represented by products. That's the Cartesian product, unqualified times, all possible pairs. You can use tensor products, which are looking at like vectors and matrices, looking within objects. But the basic one we're concerned with is the Cartesian product, which is just taking each object at its surface level. Pullbacks are qualified times, so you get that subset of the product which satisfies a particular relationship.
So it's called a pullback because you're pulling into a smaller category something.
Yes, that's right. Union, unqualified, that's a plus. It's disjoint, so you can't have duplicates. So that's standard sum. And then you can have push-outs, which are a qualified plus. So it's like a pullback, but you're constructing a plus, sometimes called a direct sum. So you sum things in it. So I'm going to show now a simple pullback for the manuscript variant. This is just one, but this isn't the application as a whole. Last year I made the mistake of trying to construct that. And it's like running before you could walk. It was I don't know if I understand the diagrams myself now.
But when you push out, you said plus, but you don't mean just plus, you also mean multiply or exponentiate, anything that moves out.
But it's a plus in the context of the times.
Stuff.
It's a plus in the context of the times. So
I see, so plus means times.
no, it's in the context of the objects on the times side. You have an interplay.
On the times side,
yes.
not the times as in
You have an interplay between the times and the
Of
plus.
course, one's a multiple of the other, yes.
Yes, so there's a tension between them, if you like.
I don't get all that. No, I keep
No, so this is a pullback. And I have specified the limit separately on the left, but this S is the score, V is the variant, and O is the occasion of some performance, something like that. And you'll note the object on the left, S times OV, that is the pairing of S and V in the context of O. So that is taking a particular score with a variant and recording the occasion on which it was actually played. And so we write it that way. The O is a subscript to the times, so because it means the times is qualified by the object O in the context of O. And pi L is a projection, so that's a project left, which is projecting S times OV onto S, and the iota L is an inclusion, which is mapping S onto O. But you might say, well, why isn't S in that right-hand object? Well, I think it is. But category theory are very economical in their notation, because you can't have an inclusion of something which isn't actually there in the representation.
Can you repeat what pi?
What you just said.
Pi is a projection.
What did you say, the last thing you said before?
Inclusion.
Oh, the iota.
Yeah.
It is an inclusion arrow, which means that that S has to be included in the right-hand side.
But you said you can't have something or something.
No, so I think the right-hand side is really S plus V plus O.
So it might be closer to a division or a distinction in terms of projection.
Yes.
No, close to which?
Which is what?
So you're saying a projection, but you're talking projection in the sense of a division, as in a Leonardo projection, or in terms of a distinction, as in...
No, projection is taking part of the product. So it's left means take to the left-hand side of the product.
Thank you.
And V means take the right-hand projection.
Could you consider pi as an epimorphism and I as an isomorphism, a monomorphism? Is that what you're doing, the factoring?
Whether monic or epic, I haven't said, but pi in general is epic or can be subjective.
Okay.
So it can be a many-to-many relationship.
Okay, good.
But I'm going to come onto a restriction where sometimes you want to make it monic, which means injective.
Injective.
Yeah. So you can handle many-to-many or one-to-one representations this way. And on the lower side, pi r is V, because that's the right-hand side of the times, and the iota r takes V into the O. But I haven't actually drawn the co-limit on that side, and that's because you can't unless pi L is monic, because constructing the sum becomes degenerate. You get problems in constructing the sum, and it breaks down. And so in category theory, pi L has to be monic, one-to-one, if you're going to be able to construct the co-limit. But you could have other diagrams which had a co-limit but didn't have a limit. I'm talking here about a special case of this type of diagram. If it's going to have both a limit and a co-limit, the one diagram, then pi L has to be one-to-one.
So monic is one-to-one and epic is many-to-many?
Epic's same as subjective. So it means onto.
On-to-many.
So it has to be found.
Monic is injective, is it?
Yeah,
Okay.
yeah.
So the pi's are surjections and the i's are injections.
Yes. Yes, I is an injection.
Injection. Okay.
Yeah, that's right. Yeah. So, and the limit, you know, all these triangles have to commute in category theory, and
When you say commute, what do you mean by that?
so that really there's a line between S times OV to O, and everything has to commute there. But you'll note that the critical thing is that if iota L composed with pi L equals iota R times composed with pi R, you've got an object which you're intersecting on, and they form the relationship. So you're looking for an object O where there is a iota pi mapping on both sides. If there's an arrow from comes through S and it doesn't actually go to an O, that will not appear in the product.
Are you calling iota the I, L, and
Yeah,
I?
those peculiar labelled I's. Yeah. So the essential algebra here is that iota L composed with pi L equals iota R composed with pi R.
Commuting.
That's the critical thing.
Composition.
That's how because that means that you're selecting those arrows where both of them intersect on an object.
So can they then be collapsed into something once they commute?
No, you won't collapse it into anything. That's a diagram.
Okay.
So that's so there are quite a lot of principles there. So everything has to commute for it to be. And you can add a lot more arrows. This is actually a locally Cartesian closed category, and you can see the arrows there. Delta picks out the O object, picks out the S and V values for a particular O value. And the existential quantifier does the exist of normal logic, and the for all does the universal quantifier. So you've got those logics.
Is the delta a co-product? Is that what you mean?
Sorry?
The delta, is that a co-product?
Delta is a functor, which is actually left, it's right adjoint to the existential, and it's left adjoint to the universal. This comes from Norvier's work in 1968. So this is really the meaning of life, if you like, in category theory. If you go
the life only applies injective in this case.
no, sorry, no, this will apply if it's many to many as well.
How does the inverse work when it's many to one?
Oh, well, yes, okay. Yes, that would give a problem.
Yes, wouldn't it?
Yes. I think the inverses may not always exist.
Right, okay. So you may select one.
No, it's not specifically one-to-one, but it's, yes, there may be problems with the inverses. Yeah. So that gives you a lot of the power of category theory there, with the logic and the limit still specified.
Excuse me, can I say something? You brought up something about inverse.
Well, you sort of apply a high star there. If you want to go both ways, then you really do require just one path, because if the path of one to many, then which one you choose to go back.
Right, so...
Yeah, there could be
many to one, which one to many, which one you choose. So
it could be ethic one way and then monic the other.
But it might not exist the other one.
May not exist. Hello.
Yes. Yes, so that appears to be the intentional structure, that is the type, the definition, but there's also the extension, which are the instances. So where are they in this diagram? Or do we have to develop them in some other fanciful structure? Well, what we're going to do is each category object, we're going to expand it into a little pullback of its own. And this thing we're going to do is called a Doolittle diagram.
Why?
after push me pull you. Who said there's no humour in category?
Good stuff.
So we're going to do a bit of work here, and don't have to follow all of this, but this Doolittle diagram, if you take the score, then you have S at the top of this pullback and S at the bottom, but they're not actually the same S, or maybe they are. This is another problem with category theory, is the notation is very minimalist. like minimalist music or something like that. And so this really keeps this as a sort of craft preserved for people who've developed this. It's not too good. Anyway, we take this Doolittle diagram. We think S is the intention here, and S, the lower S, is the extension. And so this is mapping type to value. And that is a one-to-one relationship. the S there goes to, the S with pi L goes to S, and that is monic. You can only have one type for a particular value. And if that becomes monic, then with a bit of magic, we can write a colimit on this. And this diagram is both a pullback and a push-out. So diagrams can be pulled back separately, push out separately, but you can also have one diagram acting as both a pullback and a push out, but only when pi L is monic.
Good. Perfect. Understandable. So I'm not going to read out all of that. I think I've got limit and the actual objects confused in one or two places. So every node, category, object in our pullback relationship will contain an intension part and an extension part. The Doolittle structure, also known as the Purration square adhesive category. It's another nightmare of category theory, is that people have developed things, given them different names, and they've not bothered to correlate them, not like the world of chemistry, say, where if you try and claim a new natural substance, you have to go through a very exacting process. Yeah, physics is the same. There's all sorts of people calling the same thing. I mean, one of them is zitterplating. I've heard at least 3 definitions of zitterplating within this conference so far.
Now,
all over the place. Yeah.
The good thing about this is that this type of structure, the Doolittle one, they're readily embedded into a topos. So we actually are close now to our topos structure. So through the locally Cartesian closed category and these Doolittle structures. But obviously it's far more complicated in this real world. I've got one pullback. You could easily imagine 10, 20, 30 pullbacks required to actually represent this. So how do we actually expand this diagram into more detail? Well, we've got 2 methods. We've got the horizontal way, which is to paste pullbacks together. So we paste another pullback onto it. Or we can decompose a not category object in a pullback down vertically. So we've got both those facilities. This is still an experimental area, but that's to show you, if you start pasting the pullbacks, the notation gets a bit tedious, because like this is actually putting in the composer to attach to the score and variant to give information on the composer. And so that diagram, it's a single pullback containing 3 pullbacks as a whole. And that's one thing we did a lot of work in the paper that's in the ANPA proceedings, the current one. So I don't want to go into that this time. It's just going to get more and more cluttered. So data structure as a whole, let's call it a topos perf, including that locally Cartesian closed category, any decompositions of category objects, vertical, and any pastings, horizontal. And this topos will be a placeholder, I'm sure Aristotle would like to say that, for the adhesive categories defined above. So adhesive categories are Doolittle thing. Right, so this is processed within a topos now. We go into philosophy. Metaphysics is Michael's, well, that Whitehead is Michael's style. Michael Heather's a great fan of Whitehead. And of course all his flux, classical, is Heraclitus. And doing this process, transaction, in things like databases, these require 3 cycles. Basically, you make the change, and then you test the change, and if it then you evaluate the situation and decide whether to go forward or backwards. And surprisingly, this 3 cycles also comes out in our category theory idea. Oh, sorry. Too much here. Yeah, so one of the things I got interested in was processes in the brain, because I want to have some idea of when somebody's performing music, something that what actually is going on. This is not proof for anything that I've done in the paper, but it gives perhaps a bit of insight, looking at the structures required, the processes occurring, and the control of the processes. And I'm using the violin,
Now, that certainly it would be different for other instruments, possibly. When you're playing a violin, your left hand is controlling the pitch. So that's doing, so that is called intonation, and the right hand is doing bowing. And it doesn't matter whether you're left-handed or right-handed, that's still the way it's done. And that's called articulation. So if you look at the hemispheres of the brain, the left hand maps into the right-hand side, which is doing the intonation, and the right hand maps into the left-hand side, which is doing articulation. And you have to have the left hand and the right hand in alignment with each other, which people can sometimes call rhythm or whatever, but you've got to have, obviously, the two hands talking to each other in the brain. So the coordinate control is required as you move through the score. And musicians who learn early in life have an enhanced corpus callosum to accommodate the control required between these two hemispheres. Because, and so that's why some people like expensive music lessons for their children, because they think they're going to get
That's only true for guitars and the violins. Is it also true for? It's not true.
It can't be true for the piano. No.
Why not?
No, this is definitely an area for further work.
Yeah. Okay. Good with you.
Excuse me. The piano, you've got you play the chords here and the tune there, and you've got your foot pedal. So there's also
So in category theory, we would represent this as the left-hand side will be doing the articulation, that will be a functor F, and the right-hand side will be a functor G, representing intonation, and obviously those two functors are being controlled by some other part of the system, and we think that's the monad. It's consistent with the monad approach, that the monad will be actually controlling these two processes. F and G are functors, activities. So I was saying it's interesting. It doesn't prove anything, but it does give some support for the idea that, because the monad would require, as we shall see, will require tremendous mental effort, heavy load computationally. And so that's why. Anyway, let's get on and look at the monad. We have one cycle for a jointness, that's what defines the monad. And the jointness, I don't want to spend too long on this, it's a natural relationship. You can think of it like in a joint in matrix or something like that, transposition. So you have F, which is a transposition from perf to perf prime, and then you have another functor which maps back, taking you back to the starting point, but then it may not actually take you back to the starting point you had. It may differ by eta, and if you look at it the other way, you compare it out, a change which has gone from perf prime to prime through G, epsilon will represent a displacement or difference. So you have the unit of the junction and the co-unit of the junction. But basically it's a mapping between two categories and with this natural relationship between them. A monad can actually be based on an endofunctor. So endofunctor is a functor where you have the same source category and target category. So fx to y, x is the source, gy to x, x is the target. So you end up with the same. So after doing a jointness, you're dealing with the same category. So we're going to define this activity, F and G, and we're going to make them into a monad, GF, which is one, at the basic level, is one cycle of this process. And all we're doing here, I have to stress, is one step forward in the music. So we put a lot of effort into this. How we compose the thing is another matter. So we are taking the score forward one step.
So there's like one note from...
Yeah, that depends. Yes, one unit.
One
yes,
unit,
yeah. But of course we do things in threes in category theory, and the monad comes equipped with its triple, if you like. It's t cubed to t squared to t. So when you have an adjointness, GF, that is done 3 times, just like in transactions in database systems. But then you look back with the monad, and with the comonad, you go, that would be FG, you are going forward from S to S squared to S cubed. It's actually more subtle than that. So this is giving you your backward-forward representation in this one step. So this we think just to look forward a bit. Musicians do say that when they're playing, they're looking forward and backwards at the same time. And this monad, comonad structure actually captures that. So, and it also matches the database side. So these are lovely diagrams showing T cubed is GF, 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 and S cubed is FG, FG, FG. And you can see that the T cubed one is looking back, so you're looking back at doing it 3 times, and the S cubed is looking forward. So that's how you'd express them in diagrammatic form. We do everything in diagrams. Daniel Dubois doesn't like category theory, and he did say after my talk in Bonn, he said, I can't stand these diagrams. I don't know if you thought that was a rebuke, you know,
But you just laugh. Good.
So the topos perf created earlier contains the pullback plus all the further additions you've made. A single monad, comonad action takes the music forward 1 unit of performance, which, phrase or bar, 1 step. The extension will vary because obviously the notes that are played will vary, but the intention remains the same. Closure is achieved as the type is preserved. So that's 1 step. And moving from one bar line to another is determined uniquely by the adjunction or natural relationship FG. The natural relationship between 2 processes. Now we look upon it, F is the free functor, which is creative, and G is the underlying functor forcing the rules. So in that case, the bowing in the violin would be the free functor, and the intonation, where you are getting the pitch right, is applying the rules. So you have those 2 steps on a violin. So if adjointness holds over 3 cycles, eta, the unit of adjunction, measures the creativity of the step going forward, which is called rhetoric, and epsilon, the co-unit of adjunction, measures the quality of the step looking back, which we can call dialectic. And what happens if something goes wrong? Well, this is a very interesting point with music. In a database system, you would back out immediately. But something going wrong might be outstanding expression, if you're differing slightly. So you haven't got the same culture behind it as you have. But obviously you do get cases when it does get a child playing, and they lose the plot basically, and they have to resynchronize earlier back, sometimes at the beginning. But the expected adjointness must have the limits, acceptable limits of the playing, and you will have a revised adjointness. Yes, tolerance has to be given of the acceptable limits and co-limits of performance, distinguish between a wrong note and differences in expression, and failure leads to revised adjointness, a rollback in database terms. So our work is, as I said before, is most similar to the denotators one. Oh, I could mention one thing there. I did show my musician friend my paper, and she said, I can't understand a word of it. So I actually don't think it is, I think you'd have to talk through. Yes, I've already mentioned this. Playing is an intensive experience, both looking back as to what you've paid, anticipating what is to come, and our suggestion, I'm not claiming all this is absolutely cast in stone, but the monad-co-monad structure with its forward-backward nature and inherent adjointness does seem to represent it pretty well. Yes, composition, I'll go through this fairly quickly. You might think, having got this monad, that we could just, so we've got one monad, we could compose it very easily. So you've got, say, 2,000 monads in the score. Can we compose them all? And in fact, there is a problem, because MacLean and Eilenberg, in their development of category theory, hadn't assumed that these monads would be what's called Cartesian. And a Cartesian monad is a monad which involves products. And our structure does involve products, and chords, of course, are products. So when Haskell, a functional programming language, decided to use the term monad, develop it, they found there was a problem in that the monads they had didn't compose naturally. So that was a disaster. And it must be because MacLean had never considered you would want to compose Cartesian monads. Anyway, Chrysler came to the rescue. He's a Czech mathematician, and he's got a lift, a Chrysler lift, which converts the monad into a form more suitable for composition. And he defines a natural transformation which, the basic problem is distributivity in MacLean, such an elementary thing. You've got A times TB on that second line. What you should have is A times B. It is really a schoolboy error in maths because of that. And if you look at that arrow there on the right-hand side, that diagram in general, that is Chrysler's work in upgrading A times TB to TA.
Upgrading the whole category theory for it, wasn't it?
Yes. You could say that.
Yes.
Yes, I've already dealt with that. I did put in 3 or 4 slides at the end on anticipation. I hope Daniel would like those. He didn't. He doesn't. Damn category theory. I think it's basically saying what I've said before, that you've got these distinct viewpoints of anticipation in using performers and listeners. Yes, that brings in the listeners again, so I have got it somewhere in the work. And so you do have this tension building up. And we think that the forward-looking of the monad and co-monad does actually help. It's actually very subtle, the whole system. In each cycle, the monad looks forwards and then backwards, and its co-monad looks backwards and then forwards. Whereas in the overall pattern, the co-monad looks forwards at the top level, and the monad looks backwards. So it's very complex activity there, which the brain would have to handle, in our view, to be able to do it. And so I think just to summarise, topos has been established data type of choice, and the monad shows potential for processing topos. No assumption of any particular genera. And this actually could be implemented now. We're actually getting to the stage where we can implement category theory in the programming language Haskell. So that is quite a step forward. Anyway, I think
maybe 1 or 2 quick questions.
I think your model is very interesting. I'd like to wonder a bit about how it would work if the musician is improvising. Is then you would have, for example, a wider category with less constraint, like the category of just the key, or what could be played in the key. And then there is the particular melodies and ideas, a more constrained category, and some kind of adjoint functor situation between those 2 categories going on in improvisation.
yes, I think if it was very relaxed, the rules, you could reflect that in the adjointness and what you had as permitted limits and co-limits. But I think for whatever we say, we are still biased towards the classical genre, really. We accept that varies a lot, but it would need more. In principle, it could be done from adjusting the limits and co-limits in the adjoiners. And you could make it completely free.
But then there are other questions which are very interesting, like what is the idea behind a tune, right? But a musician gets an idea behind the tune when they start changing it around and then coming back to it, the composer or the improviser.
That's right.
There is an idea, there's some category in the mind in which that idea is happening.
I think that could be included in the intention extension stuff, because the intention, if you replace the S with a T, you could include in there the intention of the composer in some form. I think, any piece, you might have so many variants, but there is scope in the intention extension hierarchy to have some scope for what the composer really intended, if there is such a thing.
No, we don't not got much time for questions. Sydney.
So in the Clydesley lift, did you say that the Cartesian monads do not commute because there's a
Not
problem?
compose, naturally.
Compose with it because there's a problem with distribution.
Yes, but if we get a Cartesian, they do if they're monads which aren't Cartesian.
Okay.
But if they're Cartesian,
That's a question over there.
Yeah, what will implementing it mean?
well, it would mean that since monads occur in Haskell, and you can define categories in Haskell, then you could actually combine the two and have an implementation, which you could then use to record performances, all the different variants and things like that, and so you could have a complete encyclopedia of it all. But that's a long way off. When Haskell says it implements these things, it doesn't implement them in as general a category way as we would like.
Okay, last question.
Just a quick one. You bear into your model the idea of fluctuation, resonance fluctuations based on situational factors. For example, let's say the mood of the person playing, the skill of the individual. When I was younger, I played violin.
Yes.
And, I have a friend of mine, an Austrian conductor. He has his own conducting school, does classical music. And one of the things that I spoke to him in terms of fluctuations in the harmonics, pitch, and performance issues to do with the conditions of you playing.
They would be measured through the unit and co-user junction.
Right.
Yes. What you do with them is really up to the designer. But you might risk criticising a top-man performer who's done some very interesting variation.
Okay, thank you very much. So lunch now. Come back at 2:30. Yeah, I believe so.
And also